losses. First of all, we studied the kinetics of the electrochemical reaction, and we got overpotential on the electrodes. So we know that there is a deviation from the theoretical equilibrium value, and it turns out in losses in our device. And today we study mass transport as a possible cause, and you'll see it's a cause for other losses in our system. You will see there are different kind of, let me say, influence in our process. First of all, we have ion transport, so we focus on the ion transport. And ion transport in our system will give losses. Then we'll study the double layer capacitance, because the presence of the double layer gave a certain dynamic behavior of our system. Then we study the current in the electrolyte, how it behaves, and what's the effect on the electrical potential in the electrolyte. And finally, we'll look at what's the effect of the mass flow or reactance in our system. Okay? Okay, first of all, we were here. So here we have a known equilibrium process in which we are obtaining current from a system in which we have hydrogen and oxygen, for example. And we have a flow of electrons, a flow of H+, as you perfectly know. We have hydrogen oxidation on one side and oxygen reduction on the other side. Okay? And so the delta V we measure between the two electrodes is the difference between phi of the positive electrode, phi plus met, minus phi electrical potential in the metal of the negative electrode. Okay? Now, we know that the single electrode, so the positive and negative electrodes, have a certain potential. The potential we have here is phi met plus minus phi met of the electrolyte plus, while on the negative we have phi met minus phi of the electrolyte close to the negative electrode. And then what we said, this is till today, so far, we said if ohmic loss is null, so we have no cost for ion transport, we can assume that the two phi of the electrolyte and both electrodes are the same. Okay? So what we are saying is that if you look at the picture here, the scheme here, we have in black the equilibrium case, then we start to draw current with the two reactions I mentioned, oxidation at the negative, reduction at the positive. So we are having a certain deviation. So this phi met will go to higher values, while on the positive side, phi met will go to lower values. Okay? And we were assuming that here, far away from the electrode, here is enough, let's say, okay? Let's do here. Here we have phi electrolyte minus, and here we have phi electrolyte plus, and they are the same value, okay? In this case, if we make the difference between these two electrode potential, the first one minus the second one, what we got is this equation. Because the two electrolyte phi cancel out. Okay? And so this is equal to this one. This is where we remain last time. Now we are introducing change in the phi of the electrolyte in our system. So next step is this one. We are introducing ion transport loss. So let's look at the picture. So it's not anymore steady now, phi of the electrolyte. It's not anymore steady. Why? Because, as you know, in our case we have positive ions, H+, and positive ion move if they go to a lower potential. Okay? So in order to have H+ to move, we have to we need to have a gradient, okay, a difference, a gradient in our phi of the electrolyte. And so the lower the value of the phi electrolyte, the more attracted is H+. This is from the physical point of view. Okay, guys? This is what we are introducing today. Now, this is from the physical point of view. Then we go on with the equation, so the analytical structure of our analysis. But in order to go on, we need to introduce in our equation for in our equation for delta V, we need to introduce a certain variation, this variation of phi of the electrolyte, and it appears as a loss. Here it is. Okay? So what we are introducing is this term, where phi of the electrolyte is, in our case, we can choose, but we have to choose. So we choose to have phi electrolyte negative minus phi electrolyte positive. Okay? This is our definition of losses in the electrolyte. Now, if you take the first equation here, this one, then you subtract this one, then you subtract this one, what you get is E plus eta plus minus E minus, oh sorry, no, sorry, let's do directly with the, I don't have room enough to do that. You get these things here, okay? So the first one minus the second minus the third, okay? But let's write it in terms of phi, okay? We write it as phi, okay? What we get is phi plus met minus phi L plus minus phi net minus plus phi L minus phi L minus plus phi L plus. And so what you got is this equation, and you see that you have phi L plus, we have a minus 1 and a positive 1 here. So they will cancel out. Also the two negative will cancel out, and what we got at the end is exactly the definition we have of delta V. Phi met plus minus phi met minus. Okay? So what we are doing is to cancel out this term with this term and this term with this term. Okay? So you see that introducing in such a way the loss in the electrolyte, we are assuming this possibility, but we are still consistent with the definition of delta V. Okay? Now let's go on. And let's try to understand what's happening close to one of the electrodes. We'll look at the negative as an example. I still use hydrogen because it's easily understandable. So, and we'll look locally. What's happening in this volume here? What's happening in this volume? This volume has a certain surface. The surface of the volume we are analyzing is A. The volume, so it's a domain, okay? It has a volume, the volume is V. And inside this volume, we have a certain area of the active, of the double layer, if you like. The active surface. So the active surface is these things here. Okay? This surface is active. Is where the double layer is formed. Is where the reaction can occur. So I define the active area per volume. Certain square meter per cubic meter. Okay? And I call it SV. So, for example, if we increase the volume like this, the active area we have S is the same. We are dividing for a larger volume. Is the same. Not the small s, but the whole S is the same. While if I enlarge like this, I'm doing something else. So it depends on what is the real domain we are analyzing. Okay? So we want to be general, very general. Okay, now, when we have this reaction, our oxidation reaction, we are producing H plus and electrons. We know that the electrons will remain inside the electrode phase, the metal phase, while we know that the H plus will remain in the electrolyte phase. So when we look at what's getting out from our volume, the only species, charged species that is moving is H plus. Because we might have something else like SO4 minus, but this is steady. There is no flux of it. No production, no consumption. Do you agree with me? The only species, charged species that is somehow varying in this domain is H plus. And in practice, what's happening when we have an oxidation, this oxidation is that we have a flux of H plus getting out from our volume. Okay? And this flux for me N I is a molar flux. So mole per second divided by a specific area, and the area we are considering is A, the surface of the volume we are analyzing. So it's mole per second divided square meters. So it's a flux mole per second of H plus, but we are looking at what's happening on the surface, A. Okay? We are looking here. N is defined on that surface, that boundary. Okay? Now, related to this, of course, we have a certain current density. So we know that this is a charged species. Okay? And so a flux of H plus will translate into a current density. Okay, this is the starting point. Now let's study, let's write the mass balance for this species, H plus. And we want to be very generical, so we write it in this way. And what we are saying here in this equation, here we have the divergence. Divergence is, you know, derivative of the flux on the surface we are analyzing. Okay? Do you all remember what the divergence is? So we are analyzing here. At the end, if you like, in the we have a certain volume. This is in general. We have a flux getting in, a flux getting out. It can have a very complex shape and lines. So all these are fluxes. And so when we make the divergence, we are considering what is the net and flux getting out from our system. Okay? So it's the derivative on the calculated on the surface, considering all the directions, so all the coordinates. So it's a what is the net flux getting out? That's the point. Now then this divergence of Ni, so the variation of the flux, if you like, is due to two things. First of all, our reaction. This is our reaction. R is the reaction rate, the Butler-Volmer. The Butler-Volmer, we know we are consuming hydrogen with a certain rate. Okay? So that's related to current, if you like. We are consuming hydrogen. So if you don't look at this for a while, you say, okay, we have a certain variation of the flux, and this is due to the fact that we have a certain reaction, consuming hydrogen and producing H plus. So what we expect to have? We have a positive reaction rate because we are producing H plus. If you look at H plus here, so consider that this is H plus, okay? We are producing H plus, so this R will be positive, and what we have is a positive divergence. So we have a net flux getting out from our surface A. Okay? Pay attention that generally the reaction rate is defined on the surface active, so SV. So we have to multiply our R by SV. So what is the actual surface we have in our volume? So R is specific to the active surface. So we multiply by SV. Okay? Be consistent. In the case, instead we had, for example, a consumption. Let me set another example. We have don't look at this again. We have a consumption of our species. For example, we are at the cathode, the positive electron. We are consuming H plus. The reaction rate will be negative. So in this case, we have a situation like this in which NH plus is getting in because we are consuming it. So if we look at our volume here, we have a net flux getting in our volume. So the divergence in this is going to be negative, this is going to be negative. The divergence is negative. So I would like to remind you that divergence is defined on outlet flux as positive. Okay, but that's not the only phenomenon that alter the divergence, we have something else. We have the accumulation term. So inside our volume, we might have a change of the concentration of our species. So the concentration here, once again, let's refer to our specific case. So H plus, we can have a change of the concentration in time. Okay? So let's set another example. Let's say that we don't have any reaction at this moment. Okay? But somehow NH plus is getting out because you are consuming H plus somewhere else. Okay, for example. So you are sure that something is getting out. You have a net flux getting out. So that is positive, the divergence is positive. And so what's happening? Here we have that the concentration in time is decreasing because we have a minus in front of it. So the derivative in time of the concentration, this is the average concentration of H plus inside our volume, is decreasing. So we are consuming what's inside. Consuming, it's getting out. Okay? You have accumulated, stored amount of H plus inside your volume, and it's getting out. Of course, you can have the opposite case. You're accumulating H plus in it. So this is the very, very generic form. Okay? Problem with this? Okay? Now, let's go on. But so far, we just deal, so far, we just deal with the molar flux. But we know that related to a molar flux of a charged species, we have a current. And here it is, the so-called Faraday's law. I here wrote for electrolyte. We can relate with this equation a molar flux. Once again, this is mole per second square meter. Here, on our surface of the volume we're analyzing. And then we are translating it in a current density. This is ampere per square meters. And once again, it is specific on the area A. So it's the current density getting out here from our domain. How we correlate them? We correlate first of all with the F, Faraday constant. This is Coulomb per mole. So it's the charge of a mole of electrons. This is our reference. So we are translating, you see, moles into coulombs. And then we are using Z, that is the charge of the species we are considering. In our case, this is +1 for H plus. Okay? So we are correlating a molar flux with a current density. Every time we have a flux of a charged species, we say we have a current. Please.
If we consider the volume to be very small, that is like very near to the electrode, can we neglect the dCi by dt term?
Can we neglect what?
The
accumulation term?
If it is very, if we
No, you can't. No, because also the specific area will be very small. Not like that. It depends. You will see that you neglect it when you arrive to a steady state. That's another stuff. It depends. You can have very big gradient inside, so it's not sure you can neglect it. Okay? Okay, so far we arrived to this equation. Okay, we apply this equation, the Faraday's law, to this one. So we are translating this one thanks to this, and what we got is this equation here. So we are multiplying our terms by ZF. So I multiply the first one and into ZF, and I got JI. So this is the current density related to the species I. I can have more than one species moving. So I have in principle more current density coming from every single species that is moving. Okay? Then I'm translating R, that is the reaction rate, into a certain I. Once again, it's in the Battle of Volmar. You remember that we already have done the translation between the reaction rate, mole per second, into current density. Okay? And then finally, we are just adding here ZF. Then, what is the net current density we have in a system? Generic. In a generic system, where I told you we can have more than one shared species moving. So we have to take into account that we have more than one JI. So the net, the total current density we get is the sum of the different JI. Generally, guys, you have one. There are some cases in which, for example, flow battery, we will study that, you have more than one moving. In some cases you can neglect, some cases you have just one, some cases you have more than one, you have to take into account. So let's be generic here. Then from Monday, we go to a single technology. And so what we're doing is summing different terms like this, and what we got is something like this. So we have a general J, a general I. We have to pay attention here how you introduce I. It depends on the case. And then we have the sum of the accumulation term. So we introduce a sum over here. And in the sum, we have to take into account that Z is different for every single species we are considering. So Z is inside the sum, okay? And inside the derivative. Okay, guys. That's the generic one. Now let's go on and let's study the current in the double layer, because as you see here, sorry, just a comment. Something is not working. Okay. Just a comment. When you look at this one, or these two, you see that you have accumulation term also on J. Also on J we have accumulation term. What's that? Let's try to understand a little better what's happening. Okay? So we focus on the current in the double layer. So we are considering, let's start from this. Okay, let's study what's happening when we enable the reaction. When we start from equilibrium, time zero, then we enable the reaction, we start. So we'll look at this transient. So we're moving from the black one to the red one, and we are still considering our hydrogen oxidation reaction to simplify things. Okay? So what we know is happening is that the Phi metal is going up. Oh. Sorry. Phi metal is going up. But we have also seen that also the field electrolyte is going up. Why? Because of this. Let's go back here. Here it is. In order to have a gradient that would allow H plus to flow, we have here phi of the electrolyte is going up, while here was going down. on the opposite case. Now we are just analyze this one. Okay? You see this picture is very similar to this one. Okay? Now, let's look at our equation, the mass balance, in terms of current. So I'm just writing this coming from the previous slide, but we are applying it to this specific case. In this specific case, we have just one charge species that is moving, that is H plus. Okay? So JH plus is J. Okay? This is JH plus, but is also J. This is the only species. Then we have Butler-Volmer here. Okay? I put a O because we're looking at the oxidation, so it's a negative electrode. And then what we have here is the concentration of H plus. Okay? So let's look at this transient I told you when we enable the reaction and what's happening at the concentration. We know that the electrolyte phi is going up. If it's going up, it means that we have less H plus over there. You remember? From a thermodynamic. Yeah? So the lower the H plus, the higher the electrolyte potential. So our concentration of H plus is going down. It's going down. I put an arrow here. It means that this derivative is negative. Okay? It's going down in time. It means that the derivative in time is negative. But then we have a minus over here because it comes from this equation. I remind you that we have a minus. Z in our case is 1. Okay? So we have a minus over here. So this term is positive. So the divergence of J is higher than in the case we have just the Butler-Volmer. Okay? So we have a current that is getting out over here, and this current related to H plus is higher than the one given just by the reaction. Because what's happening is that, I remind you that the double layer behaves as a capacitor. So here we have a capacitance somehow related to the double layer. And what we are doing is changing the voltage, the delta V of this capacitor. This is what we are doing. So we can translate this equation in a form of electrical translation of it. And so we can write that we can translate this term into this one, in which we are introducing the capacitance of the double layer that need to be determined experimentally. Okay? And generally it is defined once again on the specifically to the active area of the double layer, of course. So we have to multiply by SP to have the whole value. And what's happening? We have here the electrode potential that in our case is E minus plus eta minus. This is the actual electrode potential, and it is varying. So what's happening? At the beginning we were in equilibrium. So at the beginning eta was 0. At time 0, eta was 0. Time higher than 0, eta is positive. Okay? So the variation of this electrode potential is positive. So it's increasing, the value is it's increasing. This derivative, I can clean something, this derivative is positive. And then we have all positive values, so all this is positive. Okay? So once again, the divergence of J is affected by two things, the reaction and charge and discharge of our double layer. It behaves as a capacitor. In our case, it's increasing. Okay? So we are charging our double layer. Okay, that's all. Now, we have just, so far, we analyzed just a piece, just a small domain. Now, what's interesting is to study the whole domain that includes, all the double layer. So now what we're doing is changing from this volume, the black one, to the blue one. The blue one includes, its entire double layer is included. We don't care how big it is, but what's important is that it includes all the double layer. So all the reaction is included somehow. So we are making an integral, if you like. We are making an integral here, so we are integrating this equation in the whole volume. So I am integrating all this in the whole volume, the blue one. I wrote integral on V, entire double layer is included. So what we got is that the divergence of J, it becomes I. Here it is. The overall current that is getting out from our volume. Okay? If I make an integral, I'm getting I. I'm integrating on the whole volume. Then, of course, we have an integral. I clean something. I'm integrating also this guy here, the Butler-Volmer. And what I'm writing, to be rigorous, I put an average value because I am not sure that the reaction is occurring uniformly on the surface. So I have an average value because I integrated all around. Okay? And what I'm introducing here is the overall surface S, the big S, that is the whole active area. So the whole active area that includes all the double layer. Then, this guy here remains the same. So the accumulation term in the double layer remains the same, but we have also here the whole surface of the double layer. Okay? So this is the final equation. This equation here is describing the current in our electrode. And it includes also the transient. So we know that At the beginning, when we enable a reaction or we change the state of a reaction, we are charging or discharging our double layer. So when we change the potential of our electrode, we have a transient in which we charge or discharge the double layer. And so we have a further current term. This further current term is strictly related to this transient. And this transient, you will see, is pretty fast. Generally, is milliseconds. Okay? So it depends on the application you are studying. In some cases, this is very important. So if you are using, for example, batteries to follow, as a reserve for the frequency grid, so you are changing very fast, hundreds of hertz, kilohertz. You are changing the potential of your battery. Oh, the double layer is relevant. If you are using a fuel cell or a battery to drive a motor in a car, it might be relevant just to study the peak of power. Okay? Otherwise, you reach in, I told you, a very short time, you reach a steady state from that point of view. From the double layer point of view, it's very fast. So once you reach this steady state, this term becomes null. Okay? So generally, in milliseconds or fraction of seconds, this term will get negligible. And then the current is strictly related to the reaction. Okay? In books, you will find, they call this one, the one related to the reaction, they call it Faradaic current. Faradaic. And they call it non-Faradaic current, the one related to the double layer. Okay? Because this is somehow related to the Faraday law. Faraday law. But we know that, to be honest, we are applying Faraday's law to everything, also to this one. So I don't like very much this term. So you are, in principle, we are applying Faraday law to every term. And they call Faraday just this one, coming from this. Okay. So what we understood, what we learned is that we have a double layer. This double layer is affecting the dynamics of our electrode. So in a very short transient, we have a capacitance related to the double layer. So in principle, you have to starting your work considering that it might be important. Then you look at that typical time of the load you are studying, and then you compare with the typical time of the transient, and then you decide if you need to take into account it or not. Okay? But now you have all the physical tools to work in it. Now let's go outside the double layer. What's happening? What's happening when we are far away? We are not including the double layer. I remind you that the double layer is very tiny. It's very tiny. Nanometers, few nanometers. Okay? So as soon as you don't include the surface, okay, if you move millimeters or even microns from the double layer, you don't have any more this effect. Okay? And if you remember, I told you that the double layer will have there is a linear part and then an exponential part, and including also the exponential part, we are talking about nanometers. Okay? So as soon as you move a little from the electrode, you are in a condition like this. You are not including anymore the double layer effect. And here, we do the same thing, so we are including a certain surface and certain volume, but double layer is not included, so we still have N, a certain flux, and here what we can imagine is that some flux is getting in our volume, some flux is getting out. Okay? So we write the equation. Here is the equation. Then, associated to this flux, we have also current, and here it is the other equation. But now, let's introduce what's really happening in our case. So, first of all, we have the so-called electroneutrality. Electroneutrality means that locally, even if the domain is pretty small, you have a certain number of positive charge that are balanced by a certain number of negative charge. So if we are summing the concentration of a positive charge multiplied by Z, for every single species, it will give 0. Let's set an example. You have a certain concentration of H plus, Z is 1, then we have to sum the concentration of SO4 minus minus, and then we have a minus 2, okay? This will give 0. In every single volume, there is no effective charge. They are compensating. This is what's happening. Because they come, remember that they come from acids, so they dissociate, the acid dissociates. Okay? So you always have 0 charge net, if you consider all the species in the electrolyte. This is true when you are outside the double layer. If you remember, in the double layer, we have this gradient in the H plus, so in the positive or negative charge. But as soon as you move far away, a little far away, you get this electroneutrality true. So when this is true, if you look this, we have this value here. The sum of ZC. This is exactly the definition of electroneutrality. So this term is always 0. Even if it's a very strong, very, very fast transient, it's 0. It means that in our volume, if one H plus is getting out, or let's say if 2 need to get out, also one SO4 minus minus is getting out. They move coupled. If one gets in, the other gets in. Okay? So they need to be balanced. Okay? Then other point, we have no reaction here. We don't have any double layer included, so there's no reaction can occur in this volume. So R on I are both 0. So this term also is null. Both of them are uncounted. So it turns out in divergence is equal to 0. Also here same thing, no reaction. Okay? So I didn't report the full one. But it turns out from this one, same thing. So J must be constant. Okay? J must be constant. And also the flux, therefore, must be constant. This. Raise your voice.
So in the electrolyte, the condition will always will be in equilibrium.
Will be equal?
Will be in equilibrium because of electroneutrality.
No, I didn't get the term you said. Is
It's in
equilibrium. Is in equilibrium.
Electroneutrality.
Electroneutrality is not equilibrium. It's another thing. It's another thing. So you can have things. You can have a gradient in the concentration. Is no problem. You can have a change in the concentration, but when you go to a small volume, on any volume, even small, you always have that the number of charge is compensated. Positive and negative will always compensate. This is very fast.
But you said like one is always coupled.
Yeah, but this is not equilibrium. The term equilibrium is not correct. Because equilibrium is thermodynamic equilibrium. It means that you have a same concentration. But this is not same concentration. You might have a gradient in the volume. Yeah, you might have a gradient. No. No, you will see later. It's not equilibrium. Okay, guys? We'll talk later. It's okay? What time is it? Yeah, I think you can resist another 10-15 minutes. Is that okay? Are you tired? You want to do the break now, or you can wait 15 minutes? No. 15 minutes. Yeah, okay. So let's go on. But now we said now we define that we have a certain flux. But where the flux comes from? What is the driving force? So we wrote balances. These were mass balances. But what about the phenomenon that is determining the flux? Then the flux will determine a current, but what is the phenomenon determining the flux? We need some phenomenological equation to describe what is the origin of the flux, how is its intensity? Okay? Is that diffusion? So once again, we look at the physics, and we know that equilibrium in our system is given by electrochemical potential. So our system is described by the electrochemical potential. Because we said the pressure is constant, temperature is constant, we'll always assuming this. The only thing that is really varying is the electrochemical potential. So the only driving force that we might have in our electrolyte is the electrochemical potential. Do you agree with me? We have no other ways. So we start from that, our best friend in this course. So we are deriving everything from the definition of the electrochemical potential here. Okay? Also in this case, we are saying, okay, if we set a boundary or a certain area on which we define our flux, Ni, we can define to have a velocity of our species. We call the velocity omega, or W, as you like. Let's say omega. And we are assuming that we have a gradient in the electrochemical potential. So here we have a certain value of the electrochemical potential, and here we must have another one, because this is the driving force. So the driving force, I remind you the definition for us is this one. So what we are saying is that in the electrolyte we have a change of the electrolyte, of the electrochemical potential, and there is a law, Nernst-Einstein. Now always amazing to cite Einstein. Come on, we are doing real science here. Anyway, that velocity that we observe here is determined by the gradient of the electrochemical potential, and we multiply by a certain constant, as always in transport phenomena. In this case, Nernst-Einstein equation, so the two guys, define this as the electrochemical mobility, that is this coefficient over here. So the diffusivity, D, is the diffusivity of the species we are considering in the media we are considering, okay? The diffusivity divided by RT. Generalized, this is a generalized form. Of course, we have a minus because we are considering that a negative gradient is giving a positive velocity. So we are introducing x, in this case, x is in the direction of the velocity. Okay? So that's the reason why we have a minus, as always. Huh? You are used to this kind of equation, okay? Heat transfer, diffusion, peak diffusion, they always have, also momentum, okay? They always have this form. Now, what is the net flux of a certain species I? We are multiplying the concentration. Concentration, I remind you, is mole per cubic meters. And we multiply by the velocity, omega. That is meter per second. And this guy here is exactly our flux. So we are saying that we have a velocity of the species I, and the effective flux depends on the concentration of a species. Because this is specific to this area here. So inside this volume, we have a certain concentration. We have a concentration. So what is the net flux? It will depend on how many moles are included here. Okay? So we have a velocity, but depends also on the concentration. If it's full, you have higher flux. Flux is defined on a surface. Okay? So far we are just making things from the physics, very simply, okay? Now, what we get now is to introduce our phenomenological equation here. So we are saying that this one turns out to be this one, and that's done. That's finished. In principle, that's finished. Now we are able to transform or let me say, to make explicit the different terms that are included in our electrochemical potential. So you know that the electrochemical potential will depend on the chemical part. So we have the effect of the activity, and then we have also the effect of the electric potential. So we have two things inside there. And to make it more understandable, to reason upon it, we need to make it explicit. But this is the important equation. Okay? Then we make it explicit, and the step is this one. The step is, of course, to take this one, to introduce it here, and we have a gradient. Remember that this guy here can be written as the standard condition with the zero. Then we have plus RT ln AI. Okay? So we are making the derivative of this. We are making the derivative. So the standard value, the 0, 1, doesn't change. This is fixed. So the gradient of that is 0. But what we have here is the gradient of ln AI. Can't say that. And here it is. So you see this RT will cancel out with this one when you arrive here. Okay? So what we get, the first term for us is this one. Minus C, D. We are canceling RT with the one we have there, and then we have the gradient of ln AI. And then we have the second term related to the electrical potential, and it remains as it is, and we just remember that Z and F are constant, so we can take them out from the gradient operator, okay? So they will be here. So we see that we have effect of the activity and effect of the potential. Now let's make a further step to make it more understandable. We can calculate the gradient of the logarithm. Okay, the step is I take just the gradient, take all this guy here, and we have minus Ci di. We have the gradient of ln AI. What is the gradient of ln AI? We have 1 on AI. This is the derivative. Okay? And then we need to keep the gradient of I, because I is changing. This is the first step. So this is first step. Then we can make another step, minus Ci di. We can make explicit the concentration. Okay? So we are here in an electrolyte, so we can express the activity as the, I can write it here, AI for us is the concentration of I compared to a certain reference concentration. But we need to introduce also gamma, activity coefficient, because we don't know what we're dealing with. So it's not maybe ideal solution. We want to be generic. Okay, so let's introduce this. And so what we have here is 1 over gamma Ci over C ref. And then we have the gradient of same thing, gamma Ci over C ref. Okay, now we have to make a consideration about this. So first of all, C ref is constant, is a reference, is constant. So we can take it out from the gradient and it will cancel out with the other one. Do you agree with me? This is a simple step. Then we have a more delicate step. Most of the people neglect this, and in this case it might be a problem if you neglect it. Is that the gamma, so the activity coefficient constant? So can we take it out from the gradient? No. No. Because it can be affected by the concentration itself. Generally, in our cases, the change in the concentration is not very relevant. So in the electrolyte, we don't have a very important change of the concentration. So we can assume that this is constant. But we have to remember that we have to check it. There are some cases in which we cannot do that. Okay? We have to pay attention. So what we do is to take it out, cancel out. But then what I say is that this diffusivity, somehow, just to remember that we have done this step, I put here a star, an asterisk. I put a star over there, just to remind me that I've done this simplification. So this is true in the case we have a ideal, it's not very ideal, but it's, we are not changing the activity coefficient. Okay, so what we got is minus C, D, and then we have here a C. So also the concentration will cancel out. So what we got is minus D gradient of C. Oh, come on, that's very nice. Look at this. What is this? It's the Fick law. This is the Fick law, guys. We got the Fick law. It's very long turnaround. Then we got the Fick law. But that's good. There's plenty of experience on the Fick law. Plenty of people study the diffusivity. So these two guys here were being quite smart in finding a relation using, come on, Ernst and Dyson. They find that diffusivity is dominating here. So here we have diffusion. Here it is. But pay attention. I just put here corrected for non-ideality. So please remember that this diffusivity in some cases might be correcting, taking into account that the activity coefficient is varying. But we always know that the diffusivity coefficient might be affected by the concentration. When you are dealing with non-dilute solution and things like that. Okay. So we got the diffusion. So this is for very, very advanced analysis or very, very accurate analysis. Then we got the diffusion, but this is not the only term. There is another term. Let's go with the other one. So let me clean this. Let me clean this. Now we have this one here. At the second term, we keep it as it is. The second term is simple. I just rearrange the position of the terms to make a little confusion. But that's the only thing. I just put the Z in front of it, and then I just rearrange the position. Yeah, to make a little confusion. And we call this term migration. Migration. So we have another phenomenon that is occurring. That is generally, we are not used to that. We are not used to that. Okay? And the migration, of course, is affected by the gradient of the electrical potential you see. And what is important, of course, is the charge. That will give you the direction. If it's positive, you go towards low electrical potential. The species will move in that direction. If it's negative, the opposite. Okay? And it depends once again by the concentration. Depends on the concentration. Okay? Because once again, you remember we have the concentration applied here. So the concentration is still present. Then finally, I added something else. I added also convection. Why? Because we can have a general flux of the, a general flow, of our electrolyte. So in addition to this driving force, we can have something that's in addition to this. So there is a macroscopic flow of our electrolyte. So if you fix your volume, but then you have an overall flow, let's call it like this, species will move and get in our system. So this flux, this flow, is not given by the driving force. We are just pushing the electrolyte in. And so in our, when you look at our N, we might have an effect of this convection term. Okay? That's all, guys. I think we can stop here. Yes, we stop here.